All right, lesson 220, three-phase transformers, delta, delta. This lesson gets into some pretty heavy-duty math topics here. I think the easiest way here, I want to kind of explain some voltage readings. Then I'm going to lay out some formulas that you guys need to know. The book does a great job explaining everything. It does go very in-depth and can get kind of mind-boggling, but at the very least, these formulas that I pick out here are going to be very important for you guys in doing some of these worksheet questions coming up. So anyway, let's dive into this thing here. So delta connection on a transformer. So this is a delta connection. Essentially what we've done is we jump from the X1 of one coil to the X2 of the next, so on and so forth, to the next. And then we take our phase conductors off of this common X1, X2, kind of this corner connection. And what that looks like if you lay it out sort of the way it's actually going to look in the field or inside of a transformer, you're basically going to have a jumper between an X1 and an X2, another jumper between X1 and X2. Don't forget your main one all the way to the other end here. So essentially now we've sort of jumped these corners together, X1 to X2. Then lastly, you're going to come off of, it doesn't matter if it's X1 or X2, it's a common connection at this point, but you're going to drop each of your phase conductors off of that common connection at that point. So that's what this would look like sort of laid out in the field. These two are equivalent right now, right? If we were to talk about voltage readings at this point, if I take my meter and place it on A phase and B phase, I'm going to see, let's assume this is a 240 volt system here. From A phase to B phase, I would get 240. From A phase to C phase, I would get 240. And lastly, B to C, I would also get 240. This could be commonly a 480 system as well. And same thing, if I go from X1 to X2 on a coil, I'm going to get 240. Why would that be any different? Again, if we said A to B is 240, if I go from X1 to X2, I'm essentially doing the same thing, A to B. And we're going to get into the difference between coil voltages and line voltages, coil amperages and line amperages. So the first hint or the first formula I'm going to give you is that coil voltage is equal to line voltage in a delta connection. So in other words, if I take a reading from line to line, it's going to be the same as if I take it from coil to coil or end to end on a coil or a winding, right? So anyway, our next scenario. So this layout here is essentially identical to this last one here we looked at, right? Again, if we agree these are 240 volt rated coils. So let's jump back to this guy. So this is exactly the same. The only difference is now they're using two 120 volt coils in series, and together they give us 240. Because if we remember the single phase transformer lessons, two coils in series, the voltages add just like a series circuit. So these two 120 volt coils equal 240. Same thing across here, same thing across here. So the same logic applies. If I say this is a 240 volt system and take some voltage readings, A to B is 240, A to C is 240, B to C is 240. So what's the point of doing this? What's the point of showing this? So another common system, not quite as common, but there's plenty of these out there. If they add this neutral line here, so essentially they've come off the common tap between an X1 and an X2. Okay. This represents what I call a high leg system. So you guys may have seen this. If you haven't, you need to be aware, because these are they're not the most common things, but there's plenty of them out there. So you have a delta high leg is what they'd call this. So still, if I go from A to B, I get 240. A to C, I get 240. B to C, I get 240. None of those relationships have changed. But what's new is this neutral. If I read from my neutral, or let's say from A phase to neutral in this case, I'm going to see 120, okay? Because again, if you think from A phase to C phase, that's 240. Well, this neutral is exactly halfway to that, so I'm going to get 120. If I read from C phase, so again, C phase all the way over here to neutral, which is here, right? I'm going to get that same 120. The same logic applies. So that kind of begs the interesting question. What am I going to get if I measure from now B phase to neutral, because you can see that's got kind of this weird path it's got to take here. And you may be inclined to say it's going to be 120 plus 120 plus another 120, so 120, 240, 360. That's actually not the case, because our phases are 120 degrees out of sync in that sine wave. This gets to be some really complicated math, but you're actually going to get 208 volts from B phase to this neutral leg here. And again, this is a specific system, it's a special system. Typically when you talk about delta connected transformers, you're just talking about this simple guy here. But I want you to be aware of this delta high leg. Okay. Interestingly enough, I don't know if it's a coincidence. I'm sure it's not if you're a real math guy, but if you look at this geometrically, if you draw this out, so my distance from B phase up here geometrically is 208 inches. If this was a 240 inch by 240 inch by 240 inch triangle, this would actually be 208 inches, interestingly enough. So I did mention the differences between coil values and line values. So again, as I said, if I took a voltage reading from A to B, that's a line voltage. Okay, don't think of like GFI's line and load. This is line, meaning like electrical lines. So when we're talking about transformer readings, line values, line voltage is A to B, A to C. Coil voltage is X1 to X2. Now in a delta system, like I said before, your line voltages and your coil voltages are the same, because if I go from A to B, or I go from X1 to X2, electrically, they're the same point. So my coil voltages will be the same in a delta configuration. What will not be the same is my current. So if I were to take an amp reading of the coil, which would be kind of through here, I would get a different value than if I took an amp reading of any one of these lines. Okay, and that's kind of a complicated answer as to why. And again, your book does a nice job explaining that. I don't need you to know why. I just need you to know that it is, and coming up next year, a formula to figure that out. So I'm going to just throw a bunch of formulas at you. Jot these down. You're going to need to know these formulas to do your worksheets here, right? So power. The three-phase power of a system is going to be equal to 1.732 times line amperage times line voltage. Essentially, this is just Ohm's law, okay? And remember what I said, anytime we're doing a three-phase calculation, you got to multiply your voltage by 1.732, okay? So three-phase power equals 1.732 times amps times volts, essentially, right? Another way to look at that, your three-phase power equals the power of any individual coil, or the single-phase coil, as long as they're equally rated, times 3. So again, each of your individual coils here has a certain wattage or volt amps applied or given or known. We could simply add these three up to give us the three-phase volt amps or power, right? If we want to find the single-phase wattage or volt amps, we could do the amperage of the coil times the voltage of the coil. Okay, and again, write all these formulas down. They will come in handy. And then sort of this guy here is the opposite of this, right? So the single phase voltage or single phase power would be equal to three-phase power divided by 3. Okay, this is just another way to achieve this. Amperage. This is where it gets a little tricky on a delta system. Your coil amperage is going to be equal to your single phase power divided by your coil voltage. Your coil amperage is going to be equal to your line amperage divided by 1.732 divided by the square root of 3. That formula right there is going to be your friend. That's easy to overlook, but keep it in mind. Another formula here, and these are all, you can achieve the same thing. I'm giving you various formulas because you may be given various info to start with. So your line amperage equals your coil amperage times 1.732. So this formula here is just the opposite of this one algebraically, right? And then the easy one here, as I said, your coil voltage is going to be equal to your line voltage. When we get into Y-connected systems next time, we're going to see some essentially the opposite of this, and it'll make sense when we get there. So I know that was a lot. Let's throw an example in here, okay? So in this case, the primary of a 112.5 kVA transformer is 480 volts delta. The secondary is 240 volt delta and is delivering 100 amps to a 3-phase load. Given these conditions, blank amps of current are flowing through each primary winding. So that was a lot of stuff. I'm going to tell you right now, they gave us some info we didn't really need. So they've told us, if we kind of work backwards, we have 100 amps on the secondary of this 240 volt transformer. So this load is 100 amps. They want to know how many amps of current are flowing through each primary winding on this side. So we're really going to sort of have to walk our way back here. And we're going to have to remember our basic Ohm's law. We're going to have to remember the formulas we just talked about. All right. So first thing we're going to do, 100 amps times 240 times 1.732. Why are we doing that? Well, we have 100 amps on the secondary. The only way we can go from the secondary back to the primary is using volt amps. That's the only value that's going to take us back to the other side of this transformer. So we're going to take 100 amps times volts equals volt amps, but again, it's 3-phase, so we need to do 100 amps times 240 times square root of 3, okay? So that gives us the volt amps on the secondary side of that transformer. Notice, I don't care what the transformer is rated at this point. I know what is being drawn on it. So this is extra information up here. So next, I'm going to take that volt amps on the secondary, and let's see if we can. We're going to roll that over to the primary side. Again, the volt amps is the only value that can cross both secondary and primary sides of the transformer. So I take my volt amps, I'm going to divide by now my primary voltage, because I want to take this back to amperage, right? So I got my 41,568 volt amps divided by my primary voltage, which is 480, times the square root of 3, because again, it's 3-phase. So that tells me now 50 amps. Now the trick here, this 50 now is my line amperage. Okay, the question asks me, what is my coil amperage? What is the amperage on each primary winding on each coil? So if we refer back to the formulas we just gave out, if we remember that our amperage on our line is going, if we take that divided by 1.732, will give us our coil amperage. In other words, coil amperage equals line amperage divided by 1.732. So we could safely say now that we have 28.868 amps on each coil. Again, you're going to see a lot of math problems, a lot of equations here. I tried to run through all the math problems using the equations I gave you. It's my opinion that there's an equation there to help you solve any of those questions in there. So it's going to take some critical thinking, but pay close attention to those formulas I gave out, and I think you're going to see a lot more success there. Again, read through that textbook. They have a lot of good stuff, but really pay attention to those formulas.